So thanks for the introduction and the opportunity to be here. So, okay, so the goal of the talk is, I mean, I understood that the majority of the audience is consisted not of mathematicians, so I tried to minimize all the technicalities and try to give an overview of how certain cohomological algebras arise from the study of the so-called Aldai-Gayotto-Tachikawa conjectures in four-dimensional supersymmetric gauge theories. And so my plan is to start from the basics and so recall what at least mathematicians mean by instanton counting. Then I recall what is the Aldai-Gayotto-Tachikawa conjecture and the relation to cohomological algebras. And finally, I mean, since it's good to say what's going on right now, I will mention about AGT conjectures for the solutions of AD singularities and corresponding cohomological algebras in those cases. And I must say that unfortunately I will try to provide all the mathematical definitions of these physical quantities that I will introduce, but then I will not comment about their physics origin. So let me start by then what I mean by instanton counting. And so in order to understand what I mean by that, I needed to introduce the so-called instanton moduli space. And so we fixed two positive positive integer numbers, R and N. And then one considered the following moduli space is the moduli space that parameterizes a quadruple A, B, I, J, and they satisfy this equation, the commutator between A, B plus Ij equal to 0, and this is the so-called projective relation, and then they satisfy, so I forgot to say that IB, Ij, you may see them as A and B endomorphism of Cn. I is a linear map from Cr to Cn, and then J is a linear map from Cn to Cr. Is there any way to, okay, maybe I can use my, okay, yes, perfect. And so, no, this is better. I will use this. At least, I mean, this comes out from the garden, right? And so A, B, A, J, so you see A and B, so these are matrices, and then there are these two linear maps, and so they satisfy this closed relation that in the literature is called preprojective relation, and then they satisfy a condition that is that there does not exist any proper subspace that is invariant under A and B and contains the image of I. And this is a kind of stability condition in the sense of geometric invariant theory. And then you mod out by the action of GLN, and the action of GLN is given by conjugation. Now, one point is why this is to be the relevant moduli space to consider in order to do instanton counting and what instanton counting. And so working and playing with these matrices, so first, okay, this guy is a smooth quasi-projective variety, and then this guy contains as an open the moduli space of quadruples that satisfy the relations above. So the closed relation that was the commutator between A and B plus Ij equal to 0, and then a stability relation. So in case you already forgot what was written above, it's fine. And simply preprojective would mean it's a closed relation, is equation, and this is an open relation. And then this mreg, for this mreg parameterized points that satisfy also a stability relation when you go to the transpose. Why this is relevant from the physics point of view? Because this was proved by Donaldson. This corresponds to frame SUR instantons on S4 of instanton charge n modulo gauge transformation that are trivial at infinity. And so from this point of view, what I will care about from this part of the talk is supersymmetric gauge theories on R4. So these are, and MRN will be the relevant moduli space that I need to use in order to define some mathematical quantities that have some meaning also in physics. And so again, let me go back to summarize what is again MRN. So MRN was a space of matrices that satisfy some conditions, and then inside MRN you have an open that is the moduli space of frame instantons on S4 of instanton charge n modulo Gauss transformation trivial at infinity. And so now one thing that I want to point out is that, oh yes, yeah, you can, what means framed? That means that there is some triviality condition at infinity. There is some specific behavior at infinity, the infinity point. Okay? So because if I erase this, then you are considering somehow a compact case, but here, yeah, let me see how I can reformulate. Yeah, yeah. So yeah, okay, no, okay. Let's say there is a fixed behavior of your principal bundle at the point at infinity. So, yeah, it's a point because this is what I'm going to say now. So this, so you can start from R4 and you can compactify by adding a point and you get S4. So the way that you should see the moduli space M is DRN is the moduli space of instantons on R4 in which you impose a prescribed behavior at the point at infinity. Now, from my point of view, from algebra geometry point of view, you can see that also MRN has a similar behavior. So maybe this is I don't know if you will like more of this different viewpoint. So you take R4, then you fix a complex structure, it's a C2, and then you compactify by adding a line at infinity. And so by adding a line at infinity, you get the projective plane. And so MRN or MREG, Rn is simply moduli space of rank R vector bundles on P2, first chain class is equal to 0, second chain class, so the instanton charge is equal to n, and then framed at the line at infinity means that it's trivial along the line at infinity. So anytime you see framed, means that you start, at least from my point of view, from a gauge theory on a non-compact surface, and so when you want to construct moduli spaces of objects, a priori you cannot construct moduli spaces of objects on a non-compact. So you have to compactify the surface, and then your objects, you must impose some condition at infinity. Did I convince you better? I hope so. So at least from the point of view of MRN, this is exactly what's going on. And so you have some vector bundles of rank R on P2, but then, and this, you impose that at infinity they are trivial, and so they are simply the trivial vector bundle at infinity. Now, this is with the reg, so what happens if I remove reg? If I remove reg, I pass to, instead of vector bundles, torsion-free sheaves. So if you have no idea what means a torsion-free sheaf, it's fine. So you have to imagine that it has a vector bundle on P2, but at a finite number of points. Okay, so you can say, yeah, you can imagine like that. So it's almost like a vector bundle, but it's not a vector bundle. But still, the point here is that this is the moduli space that I like, MRN. I gave you a description in terms of quadrupole of matrices. And then this is an equivalent description that is more natural from the point of view of algebraic geometry as a moduli space of sheaves on P2 with a triviality at the line at infinity. And then this is from gauge theory viewpoint is relevant because this contains the moduli space of instantons. Okay? So this is more or less the idea, right? So the idea is that now I give you this moduli space, I'm selling you, I hope that I'm trying to sell you the idea that this is a relevant moduli space to consider if you want to study physical quantities and formalize them mathematically. And now, what I mean by instanton counting, and so among all possible partition functions that one can define, and there are partition functions that arise from n equal 4 gauge theory, supersymmetric gauge theory, and I care about partition functions associated to the so-called n equal 2 supersymmetric gauge theory that they were introduced by Nekrasov. And so, from my point of view, this partition function is simply a generating series of all these integrals where you integrate a cohomological class. The gauge theory can have masses and so on, and so obviously different gauge theories will be, the properties of the gauge theory will be encoded of what is the class that you are going to integrate. And so for me, instanton counting means simply, let's compute explicitly what is this partition function. Okay, so any questions so far? So the idea is, a priori, it's better to work with, not with mreg, but to work with mrn. And then what you define as a Nekrasov partition function is simply a generating function of integrals of your favorite cohomology class that encodes some physical property. And this is what it is. So now, great. But now the problem is that before I said that MRN was smooth, but was only quasi-projective. So it's non-compact. And so, since it's non-compact, a priori defining the integration, I mean, this is not well defined. And so what Nekrasov did was to introduce in physics what is called the omega deformation. But for me, omega deformation simply means that it worked equivariantly in a way that I will define in a second. And so all the omega deformation from my point of view was a way in order to make sense of what it means to integrate a cohomology class over MRN. And since it's non-compact, you have to find a way to do that. And so how do you do this? So you define an action. You define an action of a torus. And so the torus is the torus of C2. If you remember well, I fixed a complex structure, R4 became C2, C2 contains 2 copies of C star, so this is the torus of C2. And then you have rank R vector bundles that are trivial at infinity. So they are along the line at infinity, they are the trivial vector bundle. And so you may scale the way that the vector bundle is trivial at infinity, so you may scale the framing. And so this is the formula at the level of the quadruples. Okay. Now, why we like that? Because now the fixed locus with respect to T is compact. I mean, it's only a bunch of isolated points, it's a finite set of isolated points. And these isolated points can be written down combinatorially. I'm not going to say why this is the case, but the combinatorics is simply given by Young diagrams, Young tableau partitions, and then the number of partitions depends on the rank. And then the total sum of the number of boxes, so this is the notation for the number of boxes on the Young diagram, is equal to n. And I'm assuming everyone knows what is a Young diagram. If this is not the case, let me draw a picture. So, yes. I impose a condition at infinity, and so, yeah, so the short answer is yes, but not for the usual Gieseker semi-stability condition, but for a Gieseker type condition on a moduli space of so-called frame modules or stable pairs introduced by Algebras and 20 years ago. So the datum is given by a coherent sheaf together with a map to a fixed coherent sheaf F. In this case will be the trivial line bundle at infinity. For these guys, you define a slope or a Hilbert polynomial that encodes also the fact that there is this framing, this map. It's only a map, not an isomorphism. And then what happens is that if you look at stable objects with respect to the usual Giesecker type condition for this modified Hilbert polynomial, you realize that the framing that was a map becomes an isomorphism like there, and so all these objects are stable with respect to such a stability. So I see that, so the stability means, okay, let me write it. Yeah, so it's yeah, so what I'm saying is, let me write in this way. So this is the moduli space of Giesecker type stable objects, stable pairs on P2, where a pair is given by a coherent sheaf E and a morphism from E to a fixed F. In this case, the fixed F was the trivial line bundle at infinity. And yeah, F is supported in this case. But this is a general theory. You can run a general theory. Obviously, stable pairs on P2 with fixed rank C1 equal to 0 and C2 equal to n. So the theory was developed by Algebras and 20 years ago. And in this case, this is a, yes. And for those of you that have no idea what is a Young diagram, is simply something of this form. And then you can count the number of boxes, and then if you sum up all the possible boxes, you end up with the instanton charge. So let me say one thing. Yes. 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 Fixed points. Fixed points. Let me say one thing here that maybe help clarify one thing. So when I fix the rank equal to 1, okay, this is simply Ibeskins of points on C2. Okay? If the rank is 1, it's Ibeskins of points on C2. Because an ideal, okay, this is what it is there. Okay, so yeah, these are fixed points, okay? And so the point is now you can work equivalently, and then the integral is simply defined in a equivariant way. And then simply you have the inclusion map. You pull back your favorite class, so you have to localize, where localization means that you tensor, localization, this is notation is defined below, means simply that you are tensoring by the field of fraction of this. So you take the equivariant cohomology of MRM, this is a module over the equivariant cohomology of a point, and the equivariant cohomology of a point is simply a polynomial in these variables, and then when you localize, you are simply tensoring by the field of fraction of this. And then you have to divide, so a T-abort theorem tells me that this Euler class is invertible, and so this is a formula. Why I like this formula? Because now I have a completely combinatorial formula here that depends only on these partitions, on this Young tableau, right? So this is, so at the end of the day, I start, so from my point of view, the physics enters here when you decide what kind of class you're going to integrate. And so by definition, I will say the negative partition function of pure gauge theory or gauge theory with a joint mass or with the fundamental matter and so on will be simply some integral in which there is a specific choice of alpha. And then, thanks to this formula, the partition function that I will write down is simply some combinatorial formula, okay? And then, as I said, the localize, and also later on, localize means simply that I'm tensoring by the field of fraction. Any other questions so far? Everything generalized. But then the problem is that, so these a priori generalized to all possible Nakashima curve varieties. So Donaldson studies instantons on R4, but then Nakashima and Cronheimer, for example, studied instantons on it went down on so-called Ailey spaces, right? And then they construct model, and then they provide a description of the moduli space of instanton in such a case in terms of linear data, as I did before. And so then Nakashima generalized this, and then you can have all these bunch of moduli spaces called Nakashima curve varieties. So a priori, for some choices of these Nakashima curve varieties, you can run the same argument, and I will later on comment about this. So this is very general. The problem is that obviously if you from P2 you change from P2 to another surface, the moduli space could be more complicated, the combinatorics related to the fixed locus can be more complicated, and so the actual partition function will be, I mean, more complicated to understand somehow. For example, this is what I want to say in the case of Ailey spaces. Will be the fixed points will be Young diagrams together to another datum. Because here, at one point, this is important, is the fact that C1 is equal to 0. So C1 is equal to 0 is forced by the condition that is trivial at infinity, no? But now, if you pass from instantons on R4 to instantons on an Ailey space, at infinity, it will not be any more trivial. It will be a flat connection, and so there will be some holonomy. And so this means that in the case of Ailey spaces, the C1 will not be 0. And so the combinatorics here should take care also of this information. Okay, and I will comment about this later on as well. So what should remain about these 30 minutes? The following. So I gave you a moduli space, and I claimed that this moduli space was the right one to study Nekrasov partition functions for n equal to gauge theories on R4. And then I'm telling you the idea that these Nekrasov partition functions are mathematically defined by using this formula as some integrals, equivariant integrals as some cohomology classes. Now, let me give you an example of what is this one. So, for example, if I want to do the so-called instanton part on Nekrasov partition function for pure gauge theory on R4C2, this is simply the generating function by varying the instanton charge of the integral of 1, equivariantly. And so this means simply that I have to put 1 here, and this is what I get. And obviously here I'm making n vary, so this is encoded here. So this is the Nekrasov partition function for pure gauge theory. So there is also, Nekrasov define also a perturbative part, and also there is a classical part, but for what I'm going to say next, the relevant one is this instanton part, okay? Obviously, instead of 1, you can take whatever. So, let me say this before. That will be important. So, this instanton partition function you may see as simply the generating series of the norm of this fundamental class where the pairing is given by simple integration of these two classes. And so, from the point of view of pure gauge theory, the only relevant class that enters into the game is the fundamental class. And so this is very important because later on I will give you an interpretation, an algebraic interpretation of why this is relevant from the point of view of AGT. So if you have no idea what is Alday-Gaiotto-Tachikawa conjecture, from a mathematical viewpoint, we'll translate some information, geometrical information into algebraic ones. So here, for me, the geometric information is the fact that for pure gauge theory, the Nekrasov partition function is completely encoded by the pairing of the fundamental class of the moduli space with itself. For other theories, so for example, if you consider, instead of pure gauge theory, you consider n equal to star gauge theory, and so you take a mass in the adjoint representation. For me, all of these words are translated into the fact that I am integrating the chain class of the tangent bundle of MRN. If you want to do fancier gauge theories, then what we are going to do is that you integrate a class that depends on a bundle over MRN that is encoded by this quiver Q. So out of Q and out of the masses that you can fix in the adjoint representation and the fundamental representation, you will write down a bundle, call it the bifundamental bundle, then you take the chain classes of these bundles, you integrate them, and then you get an Nekrasov partition function, the instanton part of it. And so again, for n equal to star, the relevant, the bifundamental bundle collapses to be the tangent. And in the case of pure gauge theory, so you are integrating one, and that's it. But the formulas are like the same. So, and the nice thing here is that all of this story can be written completely on a combinatorial level. And so at the end of the day, you can completely forget about the physics or the geometry, and then you look simply at partitions and generating functions depending on partitions. Okay? Yes. It's top degree, yes. No? I mean, it depends on, yeah. But this is as, T means that, okay, T means simply that I'm looking at it equivariantly. So it's a fundamental class, but in the equivariant cohomology. And then at the end of the day, this is simply this guy. This and this, it's the same thing. It's only a way to rewrite them, no? Because you are pulling back this class to any fixed points, but then it's on a fixed points, and then the only thing that remains is simply the inverse of the Euler class of the normal bundle. In this case, the normal bundle is the tangent because the fixed locus consists of isolated points. I don't know if this. Oh, yeah. One, it's for by notation, let's say. It's by notation somehow. Because for me, it's really that you are, that it's by notation. Because that obviously makes no sense equivalently what means one. Yes, this indeed, there should be like a double dots here. It's by definition, let's say, okay? Yeah, but the point is that when the reason that I chose this notation is because for pure gauge theory is the only case in which you are somehow integrating one, because in all the other theories, with the fundamental of joint matter, then you integrate something that depends on the gauge theory, no? In this case, this depends only on the geometry, from my point of view. Now, okay, so what is the Alday-Gaiotto-Tachikawa conjecture? So the Alday-Gaiotto-Tachikawa conjecture, it's simply the following. So Alday-Gaiotto and Tachikawa brought down the instanton partition function in the case of A1 quiver gauge theory with 4 masses in the fundamental representation. They wrote down the expansion in the variable q up to order 11, and they notice that this was the same thing of a quantity in conformal field theory that are the 4-point conformal block of, in this case, was a Liouville theory. Then Willard generalized this. So what they did was only for rank 2, and then Willard discovered that passing from rank 2 to rank R means simply replacing a Liouville with Toda. Now, obviously, my interest is not about the physics side of the conjecture, but rather what is the mathematics behind. And so let's address what is the mathematics behind. So again, let me also mention the following, that you can also replace, later on people replace A1 with other gauge theories, for example, n equal to star and so on. And so you can guess what should be the conformal block on the other side and so on. So, and also this can be done also in the case of pure gauge theory. In the case of pure gauge theory, Gayot alone wrote a preprint saying what should be, and this is what I'm going to address now. And so now what I want to do is to state a mathematical incarnation of this relation here. So from my point of view, so this relation says simply that there is a quantity that you define out of a moduli space, and such a quantity must have an interpretation in algebra. So when I see conformal field theory, really I don't see the conformal field theory, I see simply the symmetric algebra behind it. And so what are the relevant symmetry algebra is the WGLR algebra. And so the WGLR algebra, it's simply, in this case, it's a WGLR. So it's the tensor product of WSLR and the infinite dimensional Heisenberg algebra. So there is a infinite dimensional Heisenberg algebra, and then there is a Z-graded vertex algebra generated by these modes here. And if you have no idea what I'm talking about, then in rank 1, so WGL1 is simply Heisenberg. And if this is the first time that you see what is an Heisenberg algebra, it is an algebra generated by elements alpha n with n in z minus 0, and then a central element, and they satisfy a relation of this form. Alpha n, alpha m equal delta m plus n 0 times c, let's say. Now, in the case where the rank is 2, then you get that WSL2 is Virasoro, and then you have simply Virasoro Heisenberg. And from the point of view of physics, this corresponds to the fact that Virasoro times Heisenberg encodes the symmetry algebra of the Liouville conformal field theory. And as I said before, I am not an expert of the conformal field theory side. What I really care is the vertex algebra that arises out of it. And then my interest here is the following. I introduce a quantity out of geometry, and I wanted to reinterpret this quantity by using the symmetry algebra. How I do that? And so this is the reformulation of AGT, and this is a theorem. This was stated by Gaiotto, and this is a theorem by Schiffen-Vassereau and by Maulik-Okunkov, and 12 years ago. And then what they did was the following. So they wonder, okay, so if I want to give a physical, an algebraic interpretation to the Nekrasov partition function, the first thing that I have to do is defining a representation of my W algebra on the relevant moduli space and the relevant vector space that I use in order to define the Nekrasov partition function. So the Nekrasov partition function is an integral over classes that lives here, okay? And so in order to provide an algebraic interpretation of the Nekrasov partition function, the first thing is to see that this W algebra, so Heisenberg or Virasoro times Heisenberg, acts here, and this is what they prove. So they prove that this is a Verma module with a specific I-waist. And then the second thing that they proved was the following. So I stated before that the only thing that you need in order to write down the Nekrasov partition function for pure gauge theory was the fundamental class. Now, the Aldai-Gayotto-Tachikawa conjecture in this case tells me that this fundamental class has also an algebraic interpretation. And so what is the interpretation? It's simply, it's the so-called Gayotto state. It's called in this way because it was conjectured by Gayotto. It's a specific element in this completion of the vector space L that satisfy these two properties. And this is the reason that it's called the Whittaker vector. It's a Whittaker vector because it defines these two properties with respect to the action of the modes of the W algebra. So now the key point here is that this characterization determines uniquely G. So this means that if I give you this theorem and you have no idea what is the Nekrasov partition function for pure gauge theory, what you do is that you define it out of the Gayotto state. And then you prove that the Gayotto state coincides with the fundamental classes, but a priori you could completely forget about fundamental classes and say the pure gauge theory is, the Nekrasov partition function for pure gauge theory is given by generating functions of norms of the Gayotto state, and that's it. So this is, from my point of view, the beauty of the Aldai-Gayotto-Tachikawa conjecture, that somehow you completely forget about the geometrical origin of the partition function, and then you get that something that has a meaning in algebra, wow, I'm very, then encodes the gauge theory information. For example, in the case of n equal to star, I say that in order to define the Nekrasov partition function, you use the integral of the chain class of the tangent bundle. But now, out of the AGT, you can say, okay, I want to completely forget about this definition, and I want a completely algebraic incarnation. And indeed, this is also the case. So there is an intertwiner operator that exists, for example, in Liouville theory. You can take the trace of this Liouville operator, this intertwiner operator, and the trace of this operator gives you the Nekrasov partition function. And so in order to define Nekrasov partition function, somehow you can play completely at the level of representations of the vertex algebra, and that's it. I'm getting, okay, but I started 5 minutes later, right? So I have still 25 minutes. Now, so now what I want to say. So let me say it again, at least must remain something out of this talk. So what should remain out of this talk? So the AGT conjectures, the Aldai-Gayotto-Tachikawa conjecture, allow you to translate quantities that you define out of a moduli space, MRN, into quantities that you can write down using simply algebraic information, like the Gayotto state here, or as I said, for n equal to star, an intertwiner of the vertex algebra. And so this was proved for only rank 2 by Negutz. He proved that indeed the instanton partition function for n equal to star is given by the trace of an intertwiner for the Liouville theory. He was unable to prove it in a higher rank in for gauge theory on R4, but then if you go to 5D, it was, I mean, also you can do the same in 5D, and in 5D he was able to prove it, the same statement for any rank. Now, my understanding from the physics point of view is that it has been hard to match the conformal field theory side with Nekrasov partition function side. So in 2011, Mironov, Morozov, and Shakirov, they did it for the original conjecture. They proved it for the original conjecture, but only for epsilon 1 plus equal to 0. Later on, this is like 4 years ago. So this is only 4 years ago. This guy proved for only, this is only SU2. Only SU2, they proved it by using some probabilistic methods. So they use some probabilistic methods and so on. So the point here is that they have to prove that the integral that I showed you before match some integral that you write down out of the CFT. And they were only able to prove it 4 years ago. And this year, this guy proved it for AN quiver gauge theory, any rank here. So 2n plus 2 masses in the fundamental, but again epsilon 1 plus epsilon 2 equal to 0. How they prove it? By more or less this proof is combinatorial. So the last one is combinatorial. It's brute force computations, combinatorial computation and matching that the combinatorics of the Nekrasov partition function coincide with the combinatorics arising from CFT. So this is my understanding of how they do it. So from my point of view, the interesting part is only the part about the symmetry algebra, the vertex algebra. Why this is interesting? So this is interesting because you want to construct this representation, right? And so how you do this? So you need some way, but then they didn't do it directly. So they were unable to define directly a representation of the W algebra on the vector space that gives rise to the cohomological classes they integrate for the Nekrasov partition function. Why so? Because only, I guess, for so WGL1 is Heisenberg, so it's given by generators relation, and rank 2 is Virasoro. Virasoro is given by generators relation. WGL3 is given again by generators relation, and then there is no way to know all the relations. And so what they do is that they prove this theorem. So this is again Schiffenwasserau and Maliko-Kunkov. So let me see if I can pack, no, I cannot pack the theorem here. And so what they do is the following. So they were able geometrically, in a geometric way, in a well geometrically defined way, to define an action of a huge algebra called the Youngian of GL1. And they define, so you needed to localize with respect to the rank, this is the Youngian, and they define geometrically an action on the vector space. And then they compare the categories of representations. And they, in this way, they induce an action of WGLR on my favorite vector spaces out of an action of this affine Youngian. And in a second, I will say what is. And so the key point is that the representation of the affine Youngian I can write down explicitly. They did it. And so this is the great thing. So instead of writing down the representation of the W algebra, they use the affine Youngian of GL1, and then they use this theorem to compare representations. Great. So what is the Youngian of GL1? I hope, no, maybe Ruven say it. Did you say what is a Youngian? Okay, so what Ruven said was maybe this one. So you take Kac-Moody algebra, then you take the current algebra, then you take the universal enveloping algebra of it, you deform it, and you got the Drinfeld Youngian. Did you say in this way? Okay, not sure, but it's fine. So this is but the GL1 is not written in this way, so this is only a notation, because WGL1 is really a deformation of W1 plus infinity that is a central extension of daily algebra of regular differential operators on the circle. This is what it is. And so this is what they define. And so the point here is, so let me go to the, and then this is the, these are certain localization. Now, what is interesting in this picture? It's interesting the following. My goal is to define for any fixed R a representation of W on the vector space that is the vector space of all the cohomological classes I care, and I am unable to do that. I am able to construct a representation of this gigantic algebra, but this representation, as you see, here there is R, because it's the rank, so changing the rank will change the cohomological classes. Here there is R, and indeed R equal 1 is only Heisenberg, R equal 2 is Virasoro Heisenberg, and so on, but here the R is only in this localization, but the algebra is the same. So, and this is a discrepancy, right? Because I have always the same algebra, but then on the other hand, I needed to construct a family of representations by varying of R. How can I reconcile this? This was reconciled. And so I can also replace the right-hand side by something that does not depend on the rank. And so this is a conjecture. So you can replace the right-hand side by a so-called universal two-parameter W infinity algebra. So this was conjectured by Gaberdiel and Gopakumar. And this is a vertex algebra that for which all possible WGLR can be realized as quotients of it. So, and this was defined by Linshaw in a paper. And so the conjecture is, okay, so here it should be maybe the deformation and so on. There should be some relations between the two. So the Youngian should be related to the universal enveloping algebra of these two parameters vertex algebra. In this way, this reconciles what is written above, because then you will see that anytime you fix R, you specialize to different vertex algebras, but somehow there is one Youngian and one vertex algebra. Okay, so I have still 15 minutes left. And so what is now the point here? The point is that we are changing viewpoint, we are changing interest, because we understood that we are unable geometrically to construct a representation of the vertex algebras. We need always to find some Youngian to do that. And so because we can construct geometrically actions of the Youngian. And so the action of the Youngian is given by, can be realized, in that case, was realized in 3 different ways. So Maurico-Kunkov, I hope that at least Ruben said that the Youngian is defined by our R matrix. Did you say so? Okay. So thanks. So Maurico-Kunkov defined the Youngian by using the R matrix in a geometric way. Schiff and Vasserot define it by using some Nakajima type operators. And then Schiff and Vasserot, and then also defined by using so-called cohomological algebras. Now, still I have only 10 minutes, right? Maybe more? Okay, so I can play with a little bit more. So now, I will not define what are these Nakajima type operators, but I want to mention the following. So you won't define these operators explicitly. So what you opt for is an operator that goes from the equivariant cohomology of MRN to, let's say, the equivariant cohomology of MRN plus K, or N minus K. So the operators that one cares here are operators that will change the instanton charge. Okay? And so all these operators, Nakajima type operators, will change the instanton charge, but the rank will be fixed. And now the main point here is that this is very nice. It's you write down explicitly. This can be run explicitly, but the cohomological algebras are useful because I have no idea if I will say it, because I mean I have like yeah, we'll try. So you want to go to other gauge theories, as Pietro was mentioning, and so this is the most easy way to deal with other gauge theories. And so how we do that? So now I have to make a choice. And so the choice I have to make is if I want to define what a cohomological algebra is, but I think that in 5 minutes would be kind of pointless. And so I will simply say some slogan, and then out of the slogan we'll try to survive. And so in order to state the slogan, let me use this. So here what I want to do, how I can change the second chain class. So somehow the operator, what I will do is that I start with a vector bundle of some rank and some instanton charge, and I would like to produce another vector bundle, another instanton of the same rank, first chain class equal to 0, and then, as I said, n plus k or n minus k. So here, the only object that I can put is an object that will not change the rank, will not, the first chain class will be 0, and will have only second chain class, right? So an object of this kind would be simply an object that corresponds to a 0-dimensional. So this is 0 because I have only second chain class, a 0-dimensional sheaf on C2. Now, the cohomological algebra is an algebra that encodes in a finer way all these possible modifications. In the case of C2, what it has to encode is all the way that we modify instantons by adding and removing the second chain class. And this can be done by considering the space that parameterizes zero-dimensional sheaves on C2. And then out of it, so as a vector space will be again not the cohomology because the space is singular, but the Bohren-Moore homology of the moduli stack of zero-dimensional sheaves on C2, and then there is a multiplication that is given, but I'm not going to define. But it will be smaller. If here I change, this is what I'm going to say next in order to save some time. So here, if I want to change the second chain, if I want to change, so as you see here, changing the second chain class is equivalent, I mean, by changing only the second chain class means that I only modifying at points. What is a zero-dimensional subset? It's a point. But here, if I want to change also the first chain class, I need to modify also along one-dimensional things, along curves. So how I do that? And why this is relevant? So let me unfortunately skip. So I was too slow. So very sorry for that. So then this is I skip. Then I can comment later. So let's try to do the following. Let's try to do the following. I want to consider other gauge theories. So the gauge theory for MRN. So I want to consider other gauge theory. So MRN, if you know, great. If you don't know, I'm going to tell you, is a Nakashima quiver variety associated to the one loop quiver. And as I said before, one can replace, I want to replace this instanton moduli space with another instanton moduli space. So what I do is I now want to consider a finite D quiver, and I want to consider the moduli space of the Nakashima quiver variety associated with this one. Now, here, as you may see, there is a theta, because before there was no theta. So the theta here is because I have a stability parameter. So for example, I have a stability parameter that I call the theta resolution, for which the corresponding moduli space that now depends on V and W is the instanton moduli space of UR gauge theories on the minimal resolution of, yeah, I have to show all of it. The minimal resolution associated to, so out of Q was affine, I have a finite quiver, there is a finite group, I take the minimal resolution, and so this is an Haley space, okay? So this is the instanton moduli space on one of the possible Haley spaces is the minimal resolution of this AD singularity. Now, one can wonder what is V and what is W. An instant on R4 at infinity, the connection becomes trivial. An instant on Haley space at infinity, the connection became flat, so corresponds to a representation of the corresponding to a representation of gamma that is encoded by W. V, on the other hand, encodes what? Encodes the first chain class and the second chain class, because at least physically, I guess the point is that there are some magnetic fluxes on the instanton, and these magnetic fluxes are encoded in V. So now, if I go back here, means that I would like to change N and have also C1, and here I have also C1 prime. And so what happens here is I needed to have something that is of dimension 1 or dimension 0. So because I want to change also C1, right? Okay, so this is one of the moduli spaces that I can construct. This is the one that I care about. But then there is also the orbifold, the moduli space. No, this will be curves, complex. Complex curves. And so Haley spaces depends, this is all the story of crime, and it depends on a stability parameter. For one of them, I get the minimal resolution singularity. For another one, I get the orbifold, the C2 mod gamma. And so you can do gauge theory on orbifold, the C2 mod gamma, which means simply that you are considering gamma equivariant instantons on R4, and so you have also the other moduli space here. So there is, now in this case, I have at least two different instanton moduli spaces. But if I have two different instanton moduli spaces, you may wonder they are the same. No, they are not the same. So they are the same as differential manifolds, but they are not the same as algebraic varieties. So what means this from the point of view of gauge theory? So I have two instanton moduli spaces. One it's the instant moduli space for instantons on a minimal resolution. The other one is the instant moduli space for instantons on the orbifold C2 mod gamma. The moduli spaces do not coincide with algebraic variety. So this means that, yes, since they are diffeomorphic, the pure gauge theory non-trivially does not fill this part. So when you only consider the instanton part with the pure gauge theory, the gauge theory is the same. So the two instant partition functions are the same in a non-trivial combinatorial way. So there is a combinatorial, I mean, there is some work to do, because the combinatorics here and here is different. So the fixed points here and the fixed points here are different. But then if I take an arbitrary quiver gauge theory, will depend on how many masses I put in the adjoint, how many masses I put in the fundamental, and this will give me different partition functions. This is because these are different. So there was like 10 years ago a work by some Japanese people that they study wall crossing of these partition functions in the rank 2 case, and they wrote some formulas, and then no one cared about that. But at least they, because what they did was simply looking at the formula and see how to adjust it in a way that one was matching the other up to some factor or up to something. And so then out of this, they saw that there was some wall crossing. Why this is a wall crossing? Because theta is in a space that is divided into chambers, and so if you goes from the orbifold stability to the resolution stability, you cross a wall. And so it's natural that you see wall crossing phenomena, but this happens only when you consider quiver gauge theories in which you insert enough masses in a way that the fundamental bundle would be completely the same, okay? No, there are a lot of other chambers. So, for example, for gamma equals Z2, you have something like, so you have always this chamber, which is always the orbifold chamber. So this is, and then I believe that is this chamber. But then I guess there is something else here. So there should be another wall and so on. But no one has studied this. And so why there is this huge difference between, something happened? No, everything, no. Okay, let me plug in again. No, it was my mistake. I touched the iPad. Okay. So these two chambers are nice because you have also a shift theoretic interpretation, and this allows you to write down what are the fixed points, not only combinatorially, but also, I mean, as sheaves. In the other chambers, this is missing. So what happens, for example, if you go in from, if you start, instead of considering Z2, you consider Z4. So then you have a lot of other chambers, but then some of them are also geometric. In what sense? So you start from C2 mod Z4. So you may resolve it all, and then you get the resolution. But you can resolve it partially by adding one P1, and then you add another one. And so you have all this bunch of partial resolutions, and so the corresponding instanton moduli space are parameterized instantons on these partial resolutions. So also there you can a priori try to do the same game. This is, I guess, I don't think that this has been explored. So in that paper, I can point you out the paper, they did some checks where they put enough masses for which they saw that there was some discrepancy, and then they found that there was a factor in order to adjust and so on. Maybe it's the same, this I don't know. Maybe it's explained there. Yeah, I understand the question, and I don't know when you see. So I guess it's a, yeah, I mean, yes, because a priori, anytime you have the bifundamental bundle, this will be different. But I don't know if when you pass to the cohomology classes, you kill so much information that you don't, yeah, this I don't know. So now, in this case, so there was a conjecture by Belavin and Fagin in 2011, I don't know, something like this, in which they say, at least for type A, that the instant partition function, the other side of the conformal field theory is super Liouville. And then they translated this, then there was a paper by Belavin, Bernstein, Fagin, Levitinov, Tarnopolsky, where they also speculate about the higher rank. So it was kind of a parafermionic Toda conformal field theory. Now, and then let me conclude with that. From my point of view, the only thing that I care are vertex algebras. But before vertex algebras, the first question is about Youngians. And so because, as I said before, in order to construct a vertex algebra representation, the first gadget that I need are Youngians. And so, do I have a representation of Youngians? And the answer is yes, when you consider the orbifold one. So, and here, for example, when Q is the affine type quiver, that one is SLN hat, and so on. That one is the Kac-Moody algebra associated with the affine quiver. And so, anytime you have the orbifold, you have already the Youngian. And then you can wonder if there is an induced vertex, some vertex algebra that acts via this Youngian. And at the moment, this is, there are some people that are working about relations between affine Youngians and vertex algebra, but this has not been sorted out yet. But now the question is what's going on when you pass from this case, from the orbifold case, to the minimal resolution singularity case. In the minimal resolution singularity case, what you get is that you have some magnetic fluxes related, for the instantons. So you needed to modify instantons. You needed to modify also their Fertian class. And so at the moment, the only thing that one can say is, okay, so I need an algebra that modifies my instantons not only at points, but also along curves. But not all possible curves, because my Fertian class will depend on only on the magnetic fluxes of this guy, of the preimage of the singularity. So the C1 will only depend on this bunch of P1. And so the only thing that I need is an algebra that allows to modify instantons also along these B1s. And so the only result I can mention, and then I am already over time, is the following. So, and then I will not say what is this completion. So there is a way, so the cohomological algebra in this case will be a cohomological algebra that encodes modification along the exceptional curve inside the minimal resolution. And then this will be again some half of the Youngian as was before, but this is uncompletion. And so the completion that appears here depends on an action of the affine extended break group of Q. And so a priori, the only thing that should remain about this part is the following. Although you have two instanton moduli spaces, one for the orbifold part, one for the resolution, the one for the orbifold receive an action of the usual Youngian associated with a affine AD quiver. And then the question is only how out of it realize representation of the relevant vertex algebra for super Liouville theory, parafermionic theory, and so on. But then when you move from the orbifold to the resolution, you cannot consider the same Youngian. You have to complete it. So the completion somehow, and this is, I don't know what means in physics, or if there is some, what goes on in the physics side. So there is a completion that you have to consider, and then out of this completion, what's going on. So now, let me finish by saying that 10 years ago, people wonder about exactly, let's go up again to the equality that I was mentioning for pure gauge theory. So people were wondering about this equality and what was the implication about this equality. And so from this side, as I've written here, you have a super Liouville theory. Now on this side, the super Liouville theory will be related to super Virasoro, right? Okay, so on this side, what do you have on this side? If you look at the instanton partition function, you realize that you must have 2 copies of Virasoro, and these must be coupled. Why so? Because you have, this is the minimal resolution, this is SZ2, will be the minimal resolution of C2 mod Z2, this is fan. And so what you can do is that you can modify your instantons at this fixed point, you can modify the instanton at this fixed point, or you can modify the instanton along the exceptional curve, it is only one. And so out of modifying at one point, you get one Virasoro, then you get another Virasoro, and then you needed to couple that. So there were some 2 Polish people that they, out of the instanton partition function for gauge theory on SZ2, they wrote down an identification between a super Virasoro and 2 copies of Virasoro coupled by exactly an operator depending on modifying along this P1. So this will imply that a priori the relation about the vertex algebra and so on will be again non-trivial. So as the Yangian will have a completion when you pass from this one to this one, also super Liouville or super Toda, when you pass to this side, there will be some game that you have to play in a way to realize it differently but equivalent to the original one. And this is what I want to end. And sorry for going, no, I was on time. So this is back on. Yes. Yes. No, this is the interesting point. No, it's interesting. So I didn't want to write the completion, but, and I'm not going, I mean, I can show you, yeah, let me show you the slide, but then I will make a comment. So the interesting thing here is that, yeah, leave it with this formula, then I will tell you something. So when you move in the space of stability conditions, and so for Ailey space, you change the Ailey space. So the point is that, so for example, in that case, and then you have orb. So the only thing is that for all of these, you will have the same Yangian, but then it will be completed with a completion that should depend on the stability. Okay, so this also has some geometrical meaning. So now, why here you have these weird formulas? So somehow what is going on, it's like what happens in quantum groups. So for quantum group, you have a Drinfeld-Jimbo presentation. And then on the other side, you have the new Drinfeld presentation. And now how you relate them? Beck and Damiani tell you that in order to relate them, you need an action of the extended affine break group. So the break group action gives you exactly a way to connect them. And this is what is written there. So we take some quotients of the Yangian in which you have an action of this T, capital T, is an action of a specific element in the extended affine break group, and you can see it as similar, I mean, in analogy with what is going on here. So the point is that the Yangian up to completion will be always the same, but the cohomological algebra capture only half of it. And so we are realizing different halves. So this is what's going on. So here you have one half that will be the Drinfeld-Jimbo, let's say, and here there will be a new half that we have no idea because at the moment we are not able to write down in terms of generators relation. But from this, you may see that, for example, you can give generators out of the usual Yangian by applying this. And this is very similar to what happens in this case. Okay, now, yes, but this is a conjectural. Because in all this cohomological algebra business, unfortunately, we are only able to define associative algebra structure. Coproduct is always very complicated. So when you consider a cohomological algebra for quivers, there is also a definition of coproduct given by Davidson. But then in this case of sheaves and so on, this is still not clear. There is a work in progress in the last 2 or 3 years by Davidson and Kinjo that say that they should be able to define coproducts in a very, for a lot of different examples that it should cover also these ones. And so if you have a coproduct, and then I have a bialgebra, then out of it I can construct a Drinfeld double algebraically. And so the Drinfeld double should be, yeah, the Drinfeld double would be again, should be the Youngian, but after completion, yes. Yes. This is the op, this is the op. The op is, yeah, the op is this one, yes. But then I don't know, because I'm not an expert in vertex algebras and so on, I have no idea how this will change when you vary. So I know only this physics paper by these Polish people that they realized super Virasoro in 2 equivalent ways. But it was a non-trivial check that they did. And so when then you move, then it should be very similar. So I have no idea how the completion will play a role with respect to different realization of, of the vertex algebra. Again, also in this case, you should expect some Linshaw 2-parameter vertex algebra, and then out of it, then you can take quotients, and these quotients will depend on the rank. In this case, the rank is encoded by W. No? But this is all conjectural.